In this tutorial, we're going to go through how to do an AC analysis on our current mirror diff amp. And so the first thing we're going to do is fire up Xschem with our VTC test harness and modify it to do an AC analysis. So that was CM diff amp VTC. And so the first thing we're going to do is get rid of the VREF voltage source. And delete that. We're going to make a follower connection around our amplifier. And we have to change the DC voltage source here to include an AC component. We're going to use a magnitude of 1 volt. And we can get away with that because the AC analysis fundamentally is a linearized analysis. And so the first thing that will be done in an AC analysis is it does a DC transfer, or it does a DC operating point analysis, and it finds out where the circuit is operating. And then it linearizes the circuit about that point, and then it throws away all the nonlinearities, and it becomes a linear system after that point. And so we are free to use any size input voltage we would like that is convenient for us, and it will produce a valid result for us. So even though the gain of this amplifier may be, oh, I don't know what it was, 150, 60, something like that, and we put in 1 volt, we would get out more than the power supply. We are still able to do this with a 1 volt signal. And that's convenient because when we plot the output voltage with an input signal of a magnitude of 1 volt, we will have directly the gain of the system, and we won't have to subtract out or divide out the output or the input signal. So that's the first pro tip for doing these sorts of AC analyses. And I apparently didn't. Oh, yes, I need to put this in quotes because the value includes embedded spaces. That's what I forgot. Okay, so there is our AC voltage source. And now we're going to change this. We're going to get rid of all of this stuff. And we're going to do .AC. And then we're going to do decade. This basically gives us a certain number of points per decade of frequency. So we're going to specify maybe 20 points per decade, and then a starting frequency of 1 hertz and an ending frequency. Let's go up to a terahertz, 1E12. And then we will save all. Okay, now let us save this as a different name. So let's call this CM diff amp follower. And yes, let's overwrite that. So we will netlist and then simulate. Again, all this time is presumably parsing the model files, and that's how long it took to do the actual simulation. So now, if we like, we could plot V of V out and see what we get. Here we get something that's kind of weird. Not at all what we might expect. So the output is about 1 volt. That's fine. and then it goes down to 0 volts at some frequency, but this is definitely not what we would expect to see. We'd like to see more like a Bode plot here, but what we're actually seeing here is probably the real component of the output voltage vector, because the output voltage vector actually winds up being complex in this type of analysis because it's a linearized analysis, and we have sort of magnitude and phase information, and that is actually comes out in like a real component and an imaginary component for the voltages in the circuit. And so that's not quite what we'd like to plot. What we'd like to plot is something more like the magnitude of the output in decibels versus frequency, and we'd like to plot the phase of the output in preferably in degrees. That's sort of the standard way of doing things. And so we can do that with some built-in functions that Ngspice has. And if I flip back over to the Ngspice manual, these are some functions that we can use that are built into Ngspice. And one of these is the dB. dB of vector returns 20 log to the base 10 of the magnitude of the vector. We also have pH, which is the phase of the vector, and the cpH, which is the phase of the vector, continuous values with no discontinuities at plus or minus pi. And so what we would like to plot is probably going to be dB of V out and cpH of V out. But this is going to turn out to be in radians, and so if we want that in degrees, we can multiply by 180 and divide by pi. And so we can get what we want by saying plot dB of V out and 180 times cpH of V out divided by pi. And this isn't maybe exactly what we want, but given the range of values for the dBs and the degrees are not outlandishly out of scale with one another, out of proportion with one another, we can get away with plotting these numbers on the same scale and kind of make sense of it. We'd like actually to plot maybe on the left axis and the right axis, but I'm not quite sure how to do that in Ngspice. So this is kind of what we have. If we don't want them on two separate plots, this is kind of what we have to live with here. But we have here the magnitude is 0 dBs, which we expect for a unity gain follower out to some frequency, and the negative 3 dB frequency here, it appears to be a little bit shy of 1 megahertz, maybe it's 800 kilohertz or something, a little hard to say, 700 kilohertz. And then we start rolling off, and it looks like maybe 20 dBs per decade until we get out to about here, and then it starts rolling off at a steeper rate, maybe 40 dBs per decade. And then we hit what appear to be two zeros because we're flattening out now. That may be this frequency here, a complex pair of zeros. And you can see the phase is in phase up here 0 degrees, and then we start to see the phase maybe an order of magnitude and frequency below where we start to see the shift in gain, and then it shifts down, and then very abruptly we get 180 degrees of phase contribution from those zeros. Okay, so that's the Bode plot. If we like, we can also export the data like we did with the voltage transfer characteristics to a text file with the WR data command. So if we set WR vec names and set WR, this is the one I couldn't remember at the end of last time, single scale. It's scale. Scale is what Ngspice calls this x-axis label representing the thing that is swept. So if we only want that column appearing once instead of once per vector we write out, we want to set this variable single scale, which if we don't specify a value here, these variables are assumed to be Boolean variables, and setting it basically makes it true. So if we go WR data, we can give it a name, so we could call this CM diffamp follower dot text, and then we can put expressions in here for the different vectors we want to write out. So we can basically put dB of V out and 180 times CPH of V out divided by pi. And if we go out here, we go into .xschem simulations, we should find our text file here. And if we do gvim cm follower text, you can see that the columns have been labeled with frequency and then dB of V out and the phase here. And so we could import this into LibreOffice Calc and convert it into a CSV file, and we could import that into MATLAB or Python or whatever else we like pretty easily. You could also work with this directly if your tool supports that to do some further analysis and plotting. Maybe you'd like to make a nicer Bode plot here where the gain and the phase are in subplots vertically aligned with each other like we normally would do. Or you could do a left-hand and a right-hand axis in something like MATLAB or Matplotlib or something like that. So that's it for this tutorial. Hope it was useful, and thanks for watching.